In this video, we'll discuss about uh, the gradient descent algorithm, its geometric intuition, and then also look at the drawbacks of gradient descent and how it can be addressed by stochastic gradient descent. But first, before understanding what is a gradient descent algorithm, we need to understand what is a maxima and minima. Consider we have a uh, consider we have a function that is having it's defined like this, like in this plot. uh, like f of x is like this. So in this graph, the one with the peak, the highest peak, is called as a maxima. Like, let it be like this. Like these 2 points are called as maxima, but this is called as local maxima, and this is called as global maxima. Similarly, these 2 points are called as local minima and global minima. So the main objective of gradient descent algorithm is if the function is, say, uh, it's minimizing, say if it is argmin, so its objective is to achieve global minima. Similarly, if the function is defined with maximizing something, then its objective is to find global maxima. Depending on the type of objective of the function, the gradient descent has to work accordingly. Sorry. So now let's dive into the details of gradient descent algorithm. So like for logistic regression, or else for, let's take logistic regression. So for logistic regression, the loss function is defined as find the W where it minimizes I equals to 1 to n log of 1 plus e to the power of minus yi w transpose xi. So this is the objective function for, or the loss function for, sorry, loss function for logistic regression, right? So what it essentially states is we have to find an optimal value for w which can minimize the sum of losses for logistic regression. Uh, and over here, the way to achieve this is, um, this optimal value of w can be found by finding the gradient for gradient of L with respect to w, which is nothing but dou L by dou w. Means we are finding the derivative of the loss function. So when we take the derivative of the loss function, this would become as summation of I equals to 1 to n. Derivative of log value is 1 by log x is 1 by x, so that is nothing but 1 by 1 plus exp of minus yi w transpose xi, and we should take the derivative of this part. So e power x derivative is e power x exp of yi w transpose xi, okay, minus yi into the inside part, derivative with respect to w, and that is minus xi yi. This is the uh, derivative of the logistic regression. So we have to find a W where this minimizes and this minimum value is like for what value of W this can be 0, right? And how it actually works, the uh, gradient descent algorithm. Sorry. Uh, Consider we have the function represented as x, and say this is how x is defined as, like the function f of x is defined as, sorry, let me erase this part. uh, yeah, so the first step is to pick a random point which uh, random point from the function, say let's name it as x0, and let me extend this so that I will explain. Okay, and at this point we take the slope at point x0. Say if this is the point, and this corresponds to x0, so at this point we take the slope, and uh, this slope at this point is positive. So what we have to do is we have to find the say minimum value of this function. So essentially finding the global minimum. So how it works is we'll pick a random point x0, and after each, in the first iteration from x0 we'll go to x1, in the second iteration from x1 we'll go to x2, and so on. We'll do k iterations till this global minima, or else the optimal value of x is reached, right? So which means say from x0 we are moving to x1, x2, so on. So as you can see, uh, as the function is descending, the slope of at all these points will also decrease, which means as we are descending, say from right to left, the slope increases, and if you look at the other side, as we are descending from left to right, the slope increases. So at these points, the slope at this point is greater than this. The slope at this point is greater than this. So in the other direction, it tries to find the global minima for that function, or the optimal value of x. And this point x1 is represented as, so from point x0 we're going to x1, right? So it is x0 minus some arbitrary value r into derivative of, say, derivative of L at point x0. Excuse me. Similarly, the point x2, we are moving from x1 to x2, right? It's nothing but x1 minus arbitrary value r into derivative of the loss function at point x1. Like this, so on, uh, will move till the optimal value for x star is found. Or else we can represent that x star as xi equals to xi minus 1 minus r into derivative of loss function with respect to xi minus 1. And yeah, we'll do this process till my uh, like 1 second, where is this? Yeah, we'll do this process till we find a value xi whose derivative is almost equivalent to xi plus 1. Till that value of xi, we will do the iterations. Now, like, so as you can see, this is an uh, update. Like this value keeps on updating, right? The uh, like the if you consider this the old value, xm like xi minus 1 will also have xi minus 2 minus r into dl by x at xi minus 2, right? So this value keeps on updating. So if we have say if the data set had 1 million data points, then this to find the optimal value x star, this I there can be 1 million iterations, which is very uh, computing heavy and time consuming, right? So to overcome this issue, we have something called as stochastic gradient descent. Stochastic gradient descent. What stochastic gradient descent does is, like we uh, from the 1 million data set, 1 million data points, for each iteration, say we saw x1 x2 so on, right? Those are the iterations. So for each iteration I'll pick k data points randomly. This could be say 1, 10, 100, 1000 or 10k, whatsoever that we have to define. So and for each iteration these k data points will be different. Means they won't be same for all the iterations. They can be different and picked randomly from the whole data set. So essentially what happens is, from for the iterations, instead of running it for 1 million data points, we will be running our iterations for k data points. So with this, because of which it will be less computation effort that is required. Effort is required, and uh, probably it may require more iterations to achieve optimal, to find the optimal value of say x or w, whatever optimal value you're trying to find. Yeah.